Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Amol Borkar of Cadence, who's going to talk today about low-power, always-on chips. Amal, where are you seeing the low-power designs for always-on AI type of chips, and what's changing there?
Right now, as you can imagine, the AI market, computer vision market is constantly evolving. There's a whole number of new application segments opening up, and the amount of compute throughput that is required for servicing these application segments like automotive, robotics, drones, AR, VR type of usages is on the rise. So along with that, it's possible to actually provide the required computation for these application segments because the devices, the DSPs, the neural processing units, or the AI accelerators are constantly evolving too. The performance throughput to service that market is starting to become more and more feasible now. But what we are seeing in terms of opportunity recently is that there has been a lot of focus on the high end of the market, like going to the tens or hundreds of TOPS processing or even petaops type of processing. But as the market is increasing on the high end side, we're starting to see now an opportunity on the low end side as well. This is in the sub 1 teraops range. You're thinking maybe half a TOPS, 250 gigaops range in the low power usage. And this is quite critical for, as you said, this always on usage where you want to have some type of algorithm or running or application running on the embedded device always on all the time.
Let's take a closer look.
Sure.
Amal, what are we looking at?
I wanted to highlight, as I just mentioned, the market segments that are constantly evolving. So if you look at these vertical market segments, we've got automotive, robotics, drones, AR, VR, mobile phone type of applications. And there is a slew of different types of sensors as well as compute requirements that are required to service these type of markets. So the automotive side, it's a combination of a variety of different sensors. You have cameras, radar, LiDARs, a bunch of sensor fusion, sensor processing happening over there. On the mobile phone side, you have time of flight sensors, stereo cameras, active stereo, some type of structured light sensors, and things of that sort. And as I mentioned, that all of this adds to the high compute type of applications, because in these type of scenarios, for example, your automotive ADAS, which is your advanced driver assistance systems, you're typically dealing with multiple cameras feeding in, processing streams, which could be in HD all the way up to 4K. And that data has to be processed in real time along with your automotive safety, which is your ASIL-B, ASIL-D requirements. So for processing ADAS type of applications, you typically need the hundreds of TOPS or the petaops range. Even for the mobile phone examples or some of the high-end AR, VR usages, you're looking at probably high double-digit TOPS type of compute requirements, because for doing those very nice pictures or post-processing on the pictures that you go on Instagram or TikTok, there is a lot of compute requirement required over there. But then as we are talking about the low power usage for those always-on applications, as I would like to highlight over here, this is called the always-on island, where you require typically very, very low compute, like the sub 1 TOP, few hundreds of gigaops type of processing.
Yeah, you think about these designs, a lot of these really are the low-end compute types of designs, right? They have to be extremely low power, but increasingly they also have to have a lot more capability than they did in the past.
Yes, absolutely. These are low compute requirements, but there is a step lower than that, which you can actually think even much more lower compute requirements. So let's take an example of a standard mobile phone that's out there that has a face unlock, the ones where you hold the phone up, you don't have to press a button or anything like that. And it looks at you, it identifies your face, detects, recognizes, authenticates, and unlocks your phone. Seems like a very simple application, but you have to assume that that phone that you have in your hand is constantly running some type of an algorithm to know first if there is a face present in the scene or no. And this is where the always on usage typically comes in. So If you have the typical off-the-shelf neural networks that could be running on these DSPs or these NPUs, your mobile phone would run out of battery very fast. And that would not make it a very compelling solution for a customer, because you could enable always on, but then you would expect the customer every 2 to 3 hours to go and charge their phone. That's not going to be something very good. Versus with always on, you can assume the flow would be like there is a very simplified basic algorithm that is running on the phone to say that, hey, is there a face or no in the scene? And if there is a face present in the scene, then I'm going to activate my larger compute machine, which in this case, relatively larger, which could be a DSP, and start doing the more accurate detection, localization, recognition, and then authenticate. So even though it's a little bit more cascaded type of an approach, it would end up ensuring longer battery life with less energy utilization.
How specialized do these designs have to be? You think about an AI chip, really what you're trying to get to in a lot of these cases is very customized type of design, because you're dealing with extremely low power, trying to get to as low power as you possibly can, and also to the maximum performance per watt.
Yeah, these are typically very small machines. So we have a spectrum of products that we have designed that we target for the low end all the way to the high end or the ultra high end in Tensilica's portfolio. But recently we announced a smaller machine, which is targeted specifically for this always on low power usage. So you can think about right now, most of the DSPs that are there in the market, though they may be low power, they're typically still more in the mid range or mid power range of operating. So you really need to scale them down to very small compute capability. In a very simple sense, you can think of it like a vision microcontroller or an AI microcontroller, in the sense that you take a standard microcontroller and you put a little bit of AI smarts on it to handle that type of a workload.
Let's drill down into always on. What does this actually look like?
Let me give you an example of what always on would look like. The typical requirements for an always on system, it's something that would be constantly running or monitoring on the embedded device. It should be capable of processing inputs from cameras, microphones, or other sensors in real time. Since this is always on, we don't expect something like this to run in the magnitudes of few hundred or thousands of FPS per second. It has to be quite minimal, sometimes within the range of like 5 to 20 FPS. It should be able to handle traditional algorithms or lightweight neural networks. And the key driver being low power and low energy consumption. Because if you have high compute, but not great energy consumption, that back to this example that I used before, you would have to keep charging your device again and again. And for any battery powered device, that is obviously not very attractive to the customer. When we're talking about lightweight neural networks for these always on devices, we have to think about neural networks that were designed to run on microcontroller class of devices. And there is a more detailed topic on this, TensorFlow Lite for micro, which specifically addresses this type of usage. And what we want to make sure that we highlight also over here is that on these always on devices, you're not expected to run your traditional off-the-shelf, out-of-the-box Model Zoo networks and expect low energy consumption, because that is not a targeted usage. And to illustrate that point, this is just a high-level representation of the type of networks that you would get out of the box from most Model Zoos. And if you look at the first line, you look at a face detection or a person detection or an object detection network that you would get from a typical Model Zoo, this would have a MAC count of about 30 gigamax per inference. Versus if you wanted to run a similar network that's would be a candidate for this always on type of usage, it should have about 7 to 10 megamax per inference. So you can see the ratio is about 430x. It's quite a large difference between the type of networks that are expected to run on an always on system. Similarly, for speech and voice detection, which could be your ASR or word spotting type of algorithms, the ones that would run on your traditional DSPs or NPUs, which are from the Model Zoo, these are in the range of 200 or 300 million max per inference, versus what you would run typically on an always on system is in 20 to 30K. It's about a 10,000x difference in the size of the network. Similarly, for the gesture processing, you're looking at between 2,000 and 2,500x as the comparison difference between the type of networks that you would run on a traditional DSP versus an always on system. So the key takeaway we want to point out over here is that These networks that we're targeting for always-on devices, they are, from a topology point of view, significantly smaller than what you would just go to like a GitHub and get them from a model zoo and expect them to run on your standard always-on low-power system.
All these devices are these days connected. So always on raises some interesting challenges in terms of both security and privacy. How do you address those?
Because these always-on systems are always usually tied to some type of a authentication type of a flow. So because nowadays everybody has their lives tied to a mobile phone or some type of an edge device, providing that functionality is very critical and key, where you can operate either the algorithm or the hardware in some type of a trusted execution environment called TEE. And there has to be ways of either developing your authentication algorithms that run directly in the trusted environment, or they run from the non-secure or the rich execution environment, and they get elevated privileges to run in a trusted execution environment are very critical.
How much of what has already been developed can be reused here? So you think about DSPs. Can the DSPs, they've always been programmable, can they do enough here? Can they do the compute efficiently, or does something have to change?
Let me walk through an example of face authentication on a mobile phone. You have a person basically standing in front of the camera. The image is fed into a CPU or an apps processor where it does the detection, recognition, authentication, and it unlocks the device. So this is a good approach, nothing wrong with it. And as you can expect over here, the CPU performs face detection and recognition constantly. And when the person is authenticated, it unlocks the phone. And this can happen today with almost any device because most of the phones have a CPU on board. But as you know, that computer vision and NN algorithms are kind of specialized, so running them on a CPU is usually not the most efficient form. So a good approach on an improvement to this is to add some type of a DSP, maybe a vision DSP. So in this case, you have the camera feeding the image directly into a vision DSP or an NPU, where it does the authentication, recognition, does the detection, authentication to the CPU or the apps processor, and unlocks it for the user. This works great. There are plenty of phones that are out there in the market that have a CPU and a vision DSP. And it's quite efficient. But again, here the problem is you're running this detection and authentication algorithm constantly on an image, and there may be times when a face is not present in the scene. So this brings us to the best use case where you have an always-on type of an application. Here you have the camera feeding in to an always-on DSP. And as you notice, this image of this person is a little bit smaller. The point being, this can be a very minimal type of an image that is being sent to a DSP. So it could be a smaller resolution. Your camera could be capturing at HD or 4K. Maybe it downsizes it, or there is a small low power always on camera that is sitting alongside this, capturing an image in low resolution. Maybe it's in monochrome. It could do an ISP bypass in a very minimal form, send it over to this always on DSP. Then this DSP will probably do something as just saying, is there a face in the scene? If there is a face detected in the scene, it will send a higher resolution image to the DSP for processing, where it will do the detection, recognition, authentication, and tell the CPU or the apps processor, I have authenticated this person, now unlock the phone. This we feel is honestly the best approach because now this always on system is constantly running all the time in a low power, low energy envelope, running some very simplified face detection algorithms. It wakes up this vision DSP to do a more accurate face detection or recognition only when a face is detected. And once all those stages are done, it tells the CPU to wake up and unlock the phone for the user. So this is honestly the best energy efficiency because the always-on system is running, as you can expect, all the time. And then this vision DSP and CPU are just running when they are needed. Even though it's a more cascaded flow, you would get much better energy utilization. In summary, if you go from the left to right, going from a CPU to a CPU plus vision DSP, or a CPU plus a vision DSP plus an always-on DSP, you get increase in performance and you get a better energy savings. And this is just one example where this is usable. There are many more applications beyond face unlock where always on could be very well used.
So can existing DSPs do the same thing, or do you actually have to change something?
I like to give a very simple example. Let's say you order a pizza and it's time to go pick up your pizza. You can go pick up your pizza with a Toyota Prius, or you can go pick up the pizza in a Ferrari. At the end of the day, you're just going to go pick up a pizza. You can accomplish the same task with a much cheaper car than having an ultra high-end sports car. You don't need to clock a record lap time or go from 0 to 60 in less than 4 seconds. So if the purpose is just to go do something very simple, you might as well use a very simplified, low footprint, small device with high energy efficiency to perform that particular task.
This all has to be set in the context of other components in the system. So you have lots of data moving here. So the things you can do, yes, you can do lower resolution. You could potentially do things like compression, but you still have this network that has to be used. Is this a dedicated network? Do you have to change something here?
Just like your traditional neural networks that you have, it could be dedicated in the sense that you have one type of network that is targeted for doing the visual wake words, which is for detecting faces. There could be a similar but lightweight network for detecting people. Just like there exists on the audio side, you have lightweight networks which are used to do keyword spotting to wake up devices. In short, yeah, there could be variances in the network, but the topology could be the same, because just like your traditional neural networks, you could have one network which has a similar topology but is targeted for doing face detection, one is detected for doing pose detection, one is used for detecting people, and so forth.
One of the things about DSPs is they've always been pretty versatile in terms of being able to do many things. Are there more things you can do with these low compute DSPs?
Absolutely. We've targeted always on usage as one of the key applications of these low power DSPs. But you could think about them as any place where you require some very simple compute or reduced form of compute could be a good application. So one example could be in smart sensors. The idea being that you have an image sensor and you have this low power DSP sitting on board the image sensor itself and does some type of pre-processing. We have seen some examples where there is some form of basic computer vision or object detection that is running on the image sensor itself, and the result of it is just metadata that is sent out. The benefit of that is you're reducing the memory bandwidth, you're reducing the traffic on the system bus, because a chunk of the compute is happening on the image sensor itself, and you're just sending out low bandwidth or low bitrate metadata. Like if there's object detection, it just says things like dog or cat or person. That is coming directly off the image sensor. Another application besides that is also video doorbells, where you can avoid false identification of people or objects in the scene, because as you can expect with video doorbells, majority of the time there's probably useless information that the camera is seeing, and you don't really need to have a more compute heavy machine that is processing that entire image. In this case, this low power machine could be doing this screening or this pre-processing or filtering before it wakes up the larger DSP. And then one more example we're seeing is this AR/VR usage in augmented reality, where you could improve or enhance foveated rendering. So if you're not aware of foveated rendering, the idea is to do rendering by mimicking the visual cortex. Unlike traditional displays where you would have rendering uniform all over the scene, our human eye has specific areas where we have the best focus versus the other parts of the area which have lower quality focus. In that sense, the idea being with foveated rendering is you would have the best rendering and GPU utilization in the central parts of the image where your eye is looking, and reduce quality of the resolution of the image on the outside of the central focal point. And in order to do that, you would need to know where your eye is looking. In typical AR/VR headsets, there can be cameras located inside the headset looking at both the pupils. It's a very controlled environment because honestly, inside a headset, you don't have a lot of outside illumination coming in. It's usually shrouded, so there's typically just a small amount of infrared illumination that is being pointed at the user's eyes. So it's controlled environment, and it could be a very simple algorithm, classical algorithm of maybe feature detection or just something like a peak sort. Rather than having a very heavy compute machine doing something like a peak sort or some basic tracking, you could run this on this low power DSP, locate where the eyes are looking and in what orientation, feed that back into the GPU pipeline, and that way you can accomplish your foveated rendering task at a very high level.
Some of this is evolutionary, some of this is not, particularly on the use case. It's really sort of radical compared to where we were in the past. How much of the previous tools and software apply, and can you reuse them? And also, where are we in terms of the ecosystem for this?
Honestly, I think software is key because you can have a very powerful piece of hardware or a unique piece of hardware, but if you don't have the right tools or right software to enable your customers or partners, then you're going to be dead in the water. Having the right software tools and having the partner ecosystem to develop on it is key for success. Fortunately, at Cadence, we have an N-way programming model for a lot of our products. So moving from a high-end DSP to a low-end DSP is typically just a matter of config settings and very minimal code changes. That way, if a customer has an algorithm that they have ported to run on the DSP and works reasonably well out of the box, you can just change a couple of options and get it to run on a low-end machine. Getting it to run is one thing, but then the second part is you have to make sure that that workload is matched properly to the hardware, because otherwise then you would have the same problem where you have this very heavy neural networks that are running on a small machine and you're not really getting the maximum efficiency.
Amol Borkar, thanks for a great explanation.
Thank you, Ed, for your time, and thank you for the opportunity. Always great talking to you.